So now, now it's setting up. Okay, we are on YouTube now.
All right. So we start now, Zhen. Okay, so hello everyone. Here is Xin Bian speaking from Zhejiang University, Hangzhou, China. I'm glad to be the host for today's seminar. So we are very happy to have Dr. Yaxing Li from ETH, Switzerland, giving a nice talk on the topic of physiochemical hydrodynamics of evaporating multi-component droplets. So here's a short introduction on Dr. Li's background. He received a bachelor degree from the University of Science and Technology of China by 2014 in the subject of modern mechanics. Afterwards, he went on to Netherlands and got master and PhD degree from University of Twente. I think his supervisor was Professor Detlof Lohse, one of the most influential persons in fluid mechanics. After that, he has been working as postdoc, I think since 1.5 years or 2 years at ETH Zurich. Now he's focusing on evaporation of multi-component droplets, collaborating with co-non-operating production, and recently he has been working on particle-laden turbulence. So very, very glad, and we're looking forward. Okay, Dr. Li, you can start.
Thank you, Professor. Let me share my screen and my slides. Can everyone see well?
Yes, it's fine.
Yes, okay. Thank you for the introduction and thank you for the invitation. I really appreciate this opportunity to participate in this seminar series, which I can share some of my work with the community. As I just talked with Professor Li, this has been a while since the start of the pandemic. I haven't really talked to our colleagues for almost 2.5 years or 3 years. So I'm really glad to join this series of seminar. So today I would like to talk about some of my PhD work, which is about evaporation of multi-component droplets. So a short introduction of myself. As Professor Bian just introduced, I did my PhD at University of Twente, Physics of Fluids Group, under the supervision of Detlof Lohse and Professor Michael Voslus. And after that, I have been working at ETH Zurich, Switzerland, with Professor Filippo Coletti. I switched my research topic from small-scale droplet system to a large-scale turbulence system. Hopefully, in the future, I can also share off my current work again. But today, I would like to focus on what I was doing in my PhD. A little outline of my talk today. So in the first part, I would like to give some little motivation about why we study this topic, why it's so important, how does it relevant to industry. And then the second part, I would like to give you some examples about the multi-component system during evaporation to show you how beautiful and how complex this small, tiny single system can be. And then the last part, I would like to introduce a pretty robust method which we proposed to suppress the so-called coffee stain effect by evaporating droplet on oil-wetted surface. On the right side is my cover of my PhD thesis. If you would like to go to more details of today's talk, you can go to my thesis or go to my paper, or even I'm very welcome if you contact me directly. So a little motivation why we do this, why the topic is so important. Of course, evaporation of droplets has a lot of background. For example, you can very easily encounter it in nature or industry. But today I would like to focus on one specific industrial background, is what I did during my master and my PhD. So during the 6th year of my stay in Netherlands, I basically collaborate with an inject printing company called OSE but they were bought like around 10 years ago by Canon company. So they no longer call themselves OSA. Now they are part of Canon. They call themselves Canon Printing Production. So I basically work their R&D department. So for example, every 2 weeks or every month, I go to their department and I talk to the engineering. They tell us what they want to know, what they want to study. And then we go to our lab to study. The company is not very familiar with most of the people. It's not because it's not great. Actually, it share almost most of the market share in European market. But the reason why people are not very familiar with it is because it only produces this big machine. For example, this one is typically 10 meters long, 2 meters tall. This is professional printers. Only like big press or newspaper, they buy this to print newspaper or booklet or big posters. So people will not buy this for their home usage. But with this big machine, if you want to achieve really high printing quality and also very high printing speed, a lot of problems you need to overcome. So people may ask, nowadays at home, we already have laser printers. Why are we still interested in inkjet printing? But actually, the reality is the opposite. The future is inkjet printing. For example, OSA already decided to focus on inkjet technology as much as possible for the future, because they think inkjet printing is the future. Why is that? I'm gonna show you. So in the past, the inkjet printing just a technique for information and communication. You can basically print on newspaper, on poster, on booklet. But nowadays, with the development of technique of inkjet printing, now we already can use this as an advanced manufacture technique. Here I show you a typical case, which I personally think is a very beautiful technique. So the OSA use their very new technique, can already perfectly reproduce this, masterpiece, The Jewish Bride by Rembrandt, use their 3D printing. Basically, they scan the original work, which is in the Museum of Amsterdam. And then they use their 3D printing to perfectly reproduce all the details and texture on the surface. So it's very difficult to tell which one is the original one, which one is the fake one, because it is just 100% reproduction. But price-wise, this is much cheaper than the original one for sure, and you can buy it, even put in your living room. It's a great technique development. So nowadays with inkjet printing, you no longer just print ink drop, but for inkjet printing, there are more possibilities. You can print many different materials on many different substrates. So inkjet printing already evolved from just a communication technique into a real manufacture technique. You can do 3D printing, you can print biomedical facilities, you can do a high-tech production printing. But what is behind is the fluid dynamics. Why fluid mechanics is so important in such progress? Why we invest so much in understanding fluid mechanics in inkjet printing? The reason is very straightforward. So this is a typical inkjet printing process I just show here. You see there are many steps of a droplet be jetted and then deposited on substrate. So you have droplet be jetted out by the print head. How do they break up due to really prone to instability? How do they fly? How do they impact with the substrate? How do they coalesce with each other? How do we penetrate into the substrate? And what I was studying was number 6 step, the evaporation. But as you can imagine, the evaporation of a real inkjet drop can be very complicated. But itself is very crucial because it directly determines how good the quality of your printing. So this is a very crucial step for the inkjet printing company to understand, so they can improve their ink drop and also the printers. But a typical inkjet drop consists of multiple components. So it's a very complicated system. Normally you have solvent, co-solvent, surfactants, pigments. They all have different properties. They have different viscosity, density, surface tension, but most importantly, they have different volatility. Because they evaporate with different speed, so no matter how well you mix them very well at the beginning, when they start evaporation, always some of the components evaporate faster than the rest. And because of this selective evaporation, it's gonna lead to inhomogeneity of the components. And this inhomogeneity will cause many interesting and complex physiochemical hydrodynamics. This is why we want to study this system. And before I go to my work, I would like to give a very brief introduction of the topic because our audience is pretty broad. So probably not everyone very familiar with this topic. So a typical droplet, for example, this is a settled droplet sitting on a solid substrate. A typical droplet evaporating to air is a diffusion limited process. The main concept is the liquid molecule wants to diffuse into the surrounding air, and the entire process we call it evaporation. And as you can see here, I put this droplet typically has a contact angle less than 90 degrees. So on the surface, you also have a inhomogeneous evaporation profile. So for this typical case, for contact angle less than 90 degrees, you will have the strongest evaporation rate on the edge and a less evaporation flux on the top of the droplet. Another very crucial physics is Marangoni effect. So basically, no matter if you have single phase droplet, you have multi-component phase droplet, they all gonna encounter this Marangoni effect because either you have a temperature gradient or you have solutal concentration gradient. All this gradient will generate a surface tension gradient, and surface tension gradient will lead to the Marangoni flow on the surface. And this Marangoni flow on the surface will also lead to the convection, and also many times very complicated convection inside the droplets. So with these two basic concepts, I think you can pretty well understand what I'm going to talk about in this talk today. So the first part of my talk, I would like to give some examples about some multi-component droplet system during their evaporation. So please allow me to go a little bit back and forth. I still want to emphasize the motivation. So basically for this big machine, every small tiny droplet is still very crucial for the final printing quality. But for every ink droplet, it has so many different components. For example, Canon, their print drop normally is water-based because it's more environmental friendly. So we always have water as one component, and then we have co-solvents, we have surfactants, and some others. For example, pigments, because eventually the paper is colored by pigments. But if you categorize all these components into two kinds, they just basically only have two categories. Some of them are non-volatile, which means they do not evaporate. And some of them are volatile, which means they do evaporate. And if you put them together, you will have the multiple component droplets. And then you deposit them on the surface, typically on paper. And then after the evaporation, only non-volatile components left. And for example, typically pigments, they will have the color on the surface to make your final printing. So we want to study this system. But the problem is that the system is too complicated. So we always need to start from very simple system from the fundamental physics point of view. So because we always have water, because of the water-based ink, so in our physical system, we always choose water as one component. And then we add different components to increase the complexity of the system. But the most easy case, of course, is the binary system, water plus another component. So the first study we have is 1,2-hexanediol and water. So hexanediol is a typical surfactant, liquid surfactant, very well used in industry, especially in inkjet printing. So the company just come to us, say, we want to know the behavior of hexanediol. and it doesn't evaporate. So we want to understand after the ink drop evaporate, how does it behavior? How does it influence the performance of our ink drop? So the first study we have is 1,2-hexanediol plus water. And the second one we study is glycerol plus water. And glycerol is taken as a co-solvent, also very well be used in the ink drop. And it also doesn't evaporate. So with this two binary system, we even simplify the system by only water evaporate. And then by understanding these two systems, we gradually increase the complexity of the system from binary to ternary. So we add little silicon oil into hexanediol and water to force a ternary system. And also we add another surfactant, which is SDS, into glycerol and water system to make another ternary system. So I'm going to introduce as the following one by one all these systems, how interesting they are. So the first system I want to discuss is the hexanediol and water system. Hexanediol and water, they can mix very well in equilibrium. No matter which concentration you put them together, they always mix. There is no separation, not like oil and water, they separate, but they mix very well, just like ethanol and water. So this makes the challenge for the measurement. If we want to know the behavior of one of those two components, how do we distinguish, how do we track them? So the technique we use is we use the different fluorescence dye to label these two components. For example, we use nail red to label hexanediol, and we use dextran to label water. These two components, these two dyes only dissolve into one component and only very little partially into another one. So with this, basically, we can very well distinguish these two. And the facility we use is confocal microscopy. We shoot a laser into the droplet, and then the fluorescence dye will absorb the laser and emit another signal. And this, because the two dyes has different emission wavelengths, so we use two channels to capture these two signals separately. By this way, we can very well see the two components, how do they distribute and the behavior. And this is a typical case I want to show you. So this is a video of hexanediol and water. So we have blue color represents water and yellow color represents hexanediol. And the beginning, they mix very well, so sort of green color, and then we let it evaporate. So the particles, the droplets start to shrink, become flat, and then all of a sudden you see this round yellow small droplet appears separate from the system, and they grow up, coalesce with the neighboring one, and eventually occupy the entire droplet, and then stop evaporation because the yellow represents hexanediol. It doesn't evaporate in this room temperature. The previous video I just showed you is a 3D video because we scan the droplet layer by layer and later we reconstructed the full 3D information. So the time resolution is pretty limited. It's around like 20 seconds. We want to see a real evolution of the nucleation. So we only focus on one layer but use the same microscope, but only focus on the bottom layer. Then we have much nicer temporal resolution. Then you can see the droplets still shrinks at the beginning, and then after a while it starts to nucleate the hexanediol. You see this beautiful yellow small droplet. They separate from the system and grow up due to the evaporation, and then they coalesce with each other, and then later fully occupy the entire droplet and stop evaporation. Okay, so what happens? Because we know, as I said before, the hexanediol and water, they mix very well. Why do they separate? So what happens during evaporation? So as I mentioned before, if you have a droplet contact angle less than 90 degrees, typically for this case, around 45 degrees, and we have water evaporate pretty fast at the contact line region. And then because of that, you have a higher hexanediol concentration at the contact line region and a higher water concentration on the apex of the droplet. Because water has a higher surface tension than hexanediol, so this will drive a Marangoni flow from the edge of the droplet towards to the top of the droplet, and also leads to a convection inside the droplet. Normally, this convection will mix the components to prevent the segregation. But however, in this case, because I said hexanediol normally taken as a liquid surfactant. So surfactant, we know after a critical concentration, no matter which concentration we have, we will not have a surface tension gradient. So this is our case. After some critical concentration, no matter how much concentration gradient we have on the surface of the droplet, we no longer can cause a strong surface tension gradient. That's why it can only cause a very weak Marconi flow and also a very weak convection inside droplet. This makes the convection is very weak. It's insufficient to mix the inhomogeneity of the distribution. Then we estimate the convection time scale, and also we estimate the evaporation time scale. If we compare these two, we find the convection time scale much larger than the evaporation time scale. This shows the convection is too slow, which insufficient to mix the droplet. And then the hexanediol will accumulate at the edge of the droplet and become more and more, and then they nucleate and separate from the system. So the first message I want you to take is that insufficient mixing will cause segregation, even in a binary system which two components mix very well in equilibrium. And the second binary system we study is glycerol and water. In this case, also only water evaporates. And then this is a typical droplet we have because for inkjet printing, we want to study tiny droplets. So basically the droplet we study normally is sub-millimeter size. And for this case, after evaporation, we should have a gradient of glycerol and water. And because it's a sub-millimeter droplet, we calculate the bond number is much less than 1. And normally, if you have a droplet system, bond number is much smaller than 1. We always think that gravity should not be relevant. And then we use the micro-PIV technique to look at the flow structure within the droplet. We have sessile droplet, and also we have the pendant droplet. But surprisingly, these two droplets, we see a completely different radial flow structures. For the sessile droplet, we have the flow structure radially inward. And for the pendant droplet, we have the opposite direction. The flow is from the center towards to the edge. This directly shows that the gravity is dominating the flow structure in this small droplet. And then we also raise the focus point from the bottom towards to the middle of the droplet. Then we can very well reconstruct the circulation from the cross section of the droplet. And then we shoot a laser sheet to look at the flow structure from the side. And we can also see this buoyancy-driven force from the bottom towards to the top of the droplet. And then not just to verify by experiment, we also do the numerical simulation to verify our hypothesis. And when we add the gravity, this is indeed very well agree with our measurement from the experiment. And also for a pendant droplet, we do the same thing. We did the experiment, we did the numerics. They are very well agree with each other. So why this happened? So we want to understand, normally the small droplet, the surface tension should play a dominating role, but why here gravity plays the most controlling role in this system? Because for experiment, we couldn't shut down the gravity. Otherwise, we have to go to aerospace. But we are on the Earth, so we take the advantage of numerics. We ask a numerical simulation, we remove the gravity in the equation, and then we see what happens. For this typical case, because glycerol is pretty viscous, so we have Reynolds number down to 10 to the power minus 4. It's pretty viscous Stokes flow inside the droplet. And you see here, we only see a weak Marconi flow on the edge of the droplet, but inside the droplet in the bulk, we barely see any visible flow. This is because the flow, the droplet is so viscous, then the interfacial flow will not influence the convection inside the droplet. And then in a relatively long time scale, the buoyancy has to play a role. For example, the water is less dense than glycerol, so the water on the bottom, which indicate by the blue color, due to the buoyancy that goes to the top, because top, due to the evaporation, we have a higher concentration of glycerol. So in this case, one, the droplet is pretty viscous and the surface flow will not very well influence the flow inside the droplet in a relatively long time scale, the buoyancy has to play a role. And we try to quantify this by non-dimensional number. What we choose is Archimedes number, because Archimedes number is the buoyancy balanced by the viscosity. The buoyancy in our case is the driven force, and viscosity is the damping force. And in some other community like turbulence, we also call it Grashof number. And then we alter the Archimedes number from pretty high to pretty low. Then we see the gravitational effect also from strong to weak. And then we even change another liquid. We use 1,2-propanediol and water. Propanediol has a larger surface tension difference with water more than glycerol. So by this way, we cannot just alter the Archimedes number. We can also have a pretty visible surface tension effect. So in this case, if you see on the left side, we have large droplet, which Archimedes number larger than 1. We have scissor droplet and pendant droplet. They have completely different flow structure, which means in this case, the gravitational effects still play the dominating role. But on the right side, when Archimedes number is less than 1, which means the gravity does not play a dominating role, then surface tension plays the dominating role. Then you see the scissor and pendant droplet, they have the same flow structure. This very well proves that in this viscous regime, the Archimedes number can be a quite good criterion to see whether the gravity is relevant or not. But of course, as I just said, the system is very complicated. If you don't have a viscous droplet, so if your surface tension can very well drive the convection inside the droplet, how to compare whether the natural convection due to the buoyancy and the Marangoni convection due to the surface tension, who is more important? Then we need a even more thorough study. But for experiment, it's very difficult because if you change liquid, you change many properties. So we also go back to numerical simulation. And in this case, we use Rayleigh number to quantify the nature convection, and we use Marangoni number to quantify the Marangoni convection. And you can see this typical phase diagram. We have many different phases. We have Rayleigh dominant phase, we have competing phase, we also have Marangoni dominating phase. And the system is so complicated. This is just one typical phase diagram with this certain contact angle. With different contact angle and different droplets geometrical configuration, the situation would even change. So if you want to know more details, you can go to our paper published on GFM last year. We have a quite thorough systematic study by numerics. And then I want to go back a little bit back to the first system, 1,2-hexanol and water. We accidentally add some silicon oil when we were doing the experiment. This is not on purpose, just accidentally we add some little silicon oil. Then surprisingly, the system dramatically changes. So this is still the same confocal videos I just showed you before, but now we add some silicon oil inside. And then immediately you find, before I play the video, you already see at the beginning of this video, you already see the segregation, the yellow color. Instead of forming those little round small droplets, it forms this regular ring. And it happens very fast. So basically this is only the first frame I had, it already appeared. And then I let it start evaporate. And you see this beautiful plume appears. And the plume is from the bottom of the droplets, climb on the top of the droplets. So this reminds of us the typical Rayleigh Taylor instability driven by gravity. Does this plume driven by gravity or is still driven by surface tension? Then the very easy improvement is still the same. We flip the droplet upside down. And then now we have the pendant droplet, and now the gravity is towards upward, but of course it's downward, but for this illustration, I make it upward just to show you this is the pendant droplet. And then we let it evaporate. We still have the rain, but instead of have this pluming, the rain just grow up and eventually fully occupy the entire droplet. There is no plume anymore. So this difference with the previous video already directly shows that the gravity do play a dominating role in this instability. So we interpreted this as really thinner instability. When we add some silicon oil, because silicon oil doesn't dissolve into water at all, and it's partially just very little dissolving into hexanol. And when we deposit the droplet on the substrate, and the silicon oil will immediately nucleate on the surface of the substrate. And this makes numerous nucleation sites for hexanol. So basically the silicon oil is just like many nucleation sites to extract the hexanol much faster than the previous case. And then when the hexanol appears, it's already formed this ring. And because the hexanol doesn't evaporate, it even separate the Marangoni effect, because we basically separate the evaporation from the strongest area, which is the edge. And then because of this, there is even less convection than the previous case I just showed you. And then in a quite long time scale, because hexanol has a lower density than water. So due to the buoyancy, it formed this really Taylor instability. And when we put the droplet upside down, the evaporation behavior is the same, but because the hexanol, which is lighter already on the top of the droplet, it will not form the instability. It just grow up because it's lighter, it's already on the top. So for these two cases, I want to show you that segregation is very common in such system. And because of segregation, it will lead to very surprising flow structure. In this typical case, it has gravitational control flow. So it's very crucial to understand segregation phenomena. And the last case I want to show you is we add the SDS with the surfactant into glycerol and water binary system, which I just showed you before. And because this combination of the liquid is also very common in inkjet printing drop. And then we study this system. We let the droplet sitting on the substrate and let it evaporate. And normally this small droplet with small bond number, it always appears as a spherical shape. And then we let it evaporate. And all of a sudden, the droplets becomes an irregular shape. This buckling happens. We don't know what happens, because normally for a liquid droplet with small size, you should always have the capillary effect dominating, which has a spherical shape. Then we put our droplet under the microscope and we look at the local details. Then we find at the beginning droplets are transparent, and all of a sudden you see this beautiful crystal appears. And then it's very quickly grow and occupy the entire drop and stop evaporation. Because crystal is solid, so sort of becomes a solid combination with liquid. So then you see this irregular buckling shape appears. We also have the measurement for the entire droplet for us to quantitatively study the growth of the crystallization. But I won't go to the details. You can go to the paper. So what is the mechanism? So basically water mixed with glycerol very well, and also water mixed with SDS very well. But SDS doesn't dissolve into glycerol, but water can help SDS mix with glycerol. So with a certain ratio of concentration, these three components can exist with each other, form an equilibrium situation. But in this system, water evaporates. Then the relative concentration of SDS become higher and higher. At that some point, it cannot stay in the system, or it cannot stay with glycerol anymore. So it separates from the system in the form of crystal. With this case, I want to take the message is that in this case, the segregation is no longer caused by the insufficient convection. It is because the limited solubility of all the components. So the take-home message of this part is that we have the key concept, which is segregation in the multi-component droplet. It can caused by insufficient mixing due to the weak convection, and also it can caused by limited solubility. And once we have segregation, no matter it's real phase separation or just the concentration gradient, it can lead to very surprising flow structure, typically in this case, a gravity controlled flow. And then All of this is because of the selective evaporation of different components, which has different volatility. And the little summary of this part is that the selective evaporation can trigger segregation, and it can cause to unexpected phase separation, flow structure, or even crystallization. But most important is that be careful with multi-component droplets, because not just in inkjet printing, but in many industrial applications, multi-component droplet with selective evaporation is very common. So this is the first part. The second part, I would like to introduce a pretty robust method we proposed 2 years ago already to suppress the very famous coffee stain effect by evaporating droplet on oil wetted surface. So coffee stain effect is a very famous phenomenon. So it was reviewed firstly by the scholars in Chicago almost 25 years ago in 1997, I believe. They published their findings in Nature, and turns out to be one of the most popular Nature paper in the last 20 years. Coffee stain effect is pretty, the mechanism is pretty straightforward. It's just once you deposit a coffee droplet on your desk, because of the roughness of the desk, it always pinning the contact line of the droplet. But the contact line, as I said, has the most strong evaporation rate. So if it has to remain pinning, you definitely need some flux or some liquid from the center of the droplet flow towards the edge to replenish the depletion of water due to evaporation. And then this replenishing outward radial flow will also carry particles towards the edge. And then, for example, in coffee, it will bring a lot of coffee particles towards the edge. And then when the particle eventually completely dried, you have a darker ring on the edge. Because of the mechanism is so simple and it doesn't require a lot, so this makes this effect so difficult to avoid. But as you can imagine, this effect is not very favorable in industry. For example, in inkjet printing, you don't want, after the drying of your ink drop, you have a darker color on the edge and the lighter color in the center. It will basically ruin the quality of your printing. So in the last 20 years, a lot of nice paper and great research groups, they try to achieve a method to suppress this coffee stain effect. They use different ways in different scenarios. For example, they use different shape of particles and use a multi-component droplet, many different ways. So why it is so important in inkjet printing, especially for my research topic. So in inkjet printing, as I just said before, the homogeneous distribution of pigments is really crucial. You don't want coffee stain effect. And also in inkjet printing, it's pretty unique that in professional printing, it's not just you put the ink drop on the paper itself. Before the printing, you always coated the surface by a primary layer. The primary layer normally is oil, consists of salt, and salt can basically destabilize the pigment in the ink drop and also help the ink drop to spread. So basically give a better performance of the ink. And then can you see some? Sorry, Hi, Professor Lee.
Yes, are you going to draw annotate on your screen?
No, I don't want. So shall I stop and reconnect? Stop sharing?
Yes, maybe you can stop sharing and share your screen again.
Because I couldn't go.
So your computer is frozen?
No, I think someone else is taking over. So he start to plot something.
Let me see. I will stop your sharing and then I'm not sure who is doing that.
Okay, now I'm okay.
Okay, can you reshare your screen?
Yes. Okay, can you see it?
Yeah, now it
Okay,
works.
now it's ready. Yeah, someone was taking over the control, so I cannot. Okay, so after it coated by the primary layer, which normally consists of oil and salt and other things, then they deposit the ink drop on this primary layer. So that's why we want to study how does the droplet behave, how do they evaporate on this primary layer. So from the fundamental physics of view, we didn't go to the very small size of the real inkjet drop because they normally picoliter size. That is too small. We cannot use a lot of optical system to study it. So we start this study with a relatively large droplet. Here you can see typically 0.5 millimeter size. And then we use the spinning coating to coat the normal glass slide. We didn't use any special glass, just a very normal one. Spinning coating with the silicone oil. And with this parameter, the typical thickness is 18 micrometer. And then we put the water droplet on this oil surface and then let it evaporate. Okay, then the experimental setup we use is this two-way observation. We have the side view, we have the bottom view. The side view, we can see the evaporation behavior. The bottom view, we can see the flow structure. And we put them simultaneously by the synchronization. So before I go to the droplet on the silicone oil wetted surface, I just show you a very typical case for a pure water droplet on a normal glass. So this is what we have. Instead of perfectly coffee rain, we have this cascade coffee rain because in reality, the substrate has a random roughness. The contact line cannot always perfectly pin at the original place. Instead, it always jump to the next position. But the idea is still the same. In every jump, they still follow this coffee stain effect, but just to follow this cascade ring structure. And this is, people call it a coffee rose. You can see it looks pretty like a rose. And you can also see this in your kitchen after you finish your coffee. You can see this coffee rose in your mug. And then we put our droplet on the lubricated substrate. And then this is the typical video we have. And you immediately can tell the difference between this one and previous one. First, the contact angle becomes much larger, and then we have this wetting edge. So then we let it evaporate, becomes flat, and then shrink, then they disappear. So we want to understand why the geometrical configuration becomes something like this. Then we look at the local information. We have this three-phase contact line. We have the air droplet surface, we have air oil surface, we have oil droplet surface. And this three-phase, three force has to be balanced. But in our case, one of the force, which is the surface force between air and droplets, is always larger than the rest of the two. So it will drag the oil all the way around the surface, fully cover the droplets, form this engulfment. And then because of this, we have a larger contact angle because the droplet no longer stay in the air, but instead it sort of partially stay in the oil. And also we have this wetting edge. Then we look from the bottom side to see how the particle behaves and how the flow structure. And you can immediately see the particle seems like doing a random motion instead of a very obvious flow structure. And also because of the shrink of the contact area, all the particles be flushes into the center. And eventually when all the droplets, when the entire droplet evaporate, all the particles left on the center of the original area. And with this, we already sort of remove the coffee stain, but still we don't have a homogeneous distribution. We only have this concentrated particle in the center. So some people already studied this with different way. They call it coffee eye. But with this, we still don't have a uniform coating. So the reason is that now the contact line is moving, the contact area is shrinking. So we want to fix the contact area. So then how to do that? We add some surfactant into the droplet. And because we add the surfactant into the droplet, then the droplet has a lower energy with the solid substrate. And the energy is lower than the energy between the oil and the substrate. So during the evaporation, the droplets do not want to shrink. It just want to stay with the original size and just become flat. By this way, we can fix the contact line. And this is another typical video we had for this case. And eventually you see from this dark shadow, the area, the final area is similar to the original area. And then we have the, this bottom view, and you can see eventually the distribution of particles is more homogeneous than the two previous cases. So how do we suppress the coffee stain effect in this way? Here is the mechanism. So a typical evaporation coffee stain effect, as I said, is due to the capillary force, the flow from the center towards to the edge and bring all the particles over there. But now we have silicone oil wetting edge on the contact line area, and silicone oil doesn't evaporate. So basically suppress the evaporation rate over there. So the flow near the contact line region even needs to go inward because the droplets become flat. And by this way, we can very well suppress the outward radial flow. So that leads to more homogeneous distribution. Can we quantitatively understand these things? Of course. So we do the PIV measurements simultaneously with the side view. And then you see here, I just show you the temporal pictures of the flow structure. And then you see most of the time, the radial velocity is pretty low. And then only in the very end, because the droplet becomes very, very flat. So some particles used to stay in the upper layer has to go to somewhere. So it flushes to one side of the droplet. So this is sort of a flaw we have for this method, but this is a rush hour phenomenon. We cannot overcome this. Hopefully in the future, we can have a better idea how to overcome this very last moment, the rush hour. So quantitatively, we can even propose a model to describe this suppression of coffee stain. So this is a typical cross-section of droplet, and we only have one small slice of the droplet. And then we have the height of this small slice. And the change of this height is due to the flux in and flux out at this very position. And also, we have the evaporation flux. And the flux within the droplet and the evaporative flux causes the height or the mass conservation of this little cross-section. And then we also have the profile of the evaporation rate, which is named by J. And we imply this J into the equation. And with some geometry relationship, we can very well resolve this radial velocity. What we need to focus on is the second part, which when R larger than the area which covered by the silicone oil. So here I show you the red areas indicate the radial flow, which predict by the equations I marked in the red square. And you can see this is the experiment data we take, and this is the theory we have. It works, they agree with each other very well. Only the little part which I just mentioned, the rush hour, some of the particle has to goes to some part because of they basically have nowhere to go. Hopefully in the future we can overcome this little parts. And then the summary of this part is we have three different cases: pure water, water on lubricated layer, and water with surfactant on this lubricated layer. Then we can achieve a suppression of coffee stain effect from into coffee eye or even homogeneous distribution. And we published this paper 2 years ago in PNAS, and you can, if you want more details, you can go to our paper. So the very last, I would like to thank all my colleagues and of course my supervisor. All the experiment I did is with Dr. Pengyu Liu and Dr. Tim Seegers, and the numeric simulation is done by Dr. Christian Diddens. And I would like to thank my supervisors, Detlev Loser, Michel Voslus, and also my supervisor in Canon, Hermann Voschhoff. Thank you very much for your attention. I would like to take any questions.
Very nice talk. Thanks, Dr. Lee. Although a very short academic career, you have been very productive. Have so many papers in top journals. So I think, Professor Lee, people can just unmute themselves, right? To ask questions.
Yes, if anyone have a question from audience, they can unmute themselves and ask a question to Dr. Yashini.
So I may start one. So when you want to compare some of your results between the simulations and your experiment, how do you make sure they are in the same system? Did you take the contact angle from the experiment you measure first? And these are the
exactly
of your continuum simulation, right?
Exactly. Exactly. So it's very difficult to for my colleague to mimic the real contact angle or the contact line movement, because this is highly based on the quality or the wetting property between the droplet and the substrate. So basically, in his simulation, he always needs my input from experiment to tell him temporarily how does the contact angle and the contact line changes.
Mm-hmm.
And then he uses the information to solve what happens inside the droplet and also between the air and the droplet.
Were they the three-dimensional simulation or two-dimensional?
Normally it's two-dimensional because my system, most of them are anti-symmetric. But in many of his own paper, like his 2017 GFM paper, he has a full 3D simulation, but of course consume more computational power. So normally in most of my papers, he did 2D simulation.
So the 2D, due to the axisymmetric, can essentially capture all the physics, right? Okay.
Exactly.
That's good.
Exactly.
Yeah. Mm-hmm.
Hi, Professor Lee. So
hi. I'm not a professor.
Yes,
yeah,
very nice work. So it's very impressive. So I have a small question about the model, and you mentioned that you predict the velocity of the radius by by using a model.
You mean this one?
Yeah.
Yes. Please.
Yeah. So maybe this one. So during the rush hour.
This one?
The previous one. Yeah, this one.
Yeah.
During the rush hour, so the fluctuation of the velocities in the experimental data, so is a little big during the rush hour. So how to understand the change of the velocity?
Yes, this is a very good question.
Thank
so
you.
basically, as you can see, most of the radial velocity you see from this plot is negative, which means it's radially inward. So basically have outward, which is positive, inward, which is negative. And the fluctuation you see in the rush hour, basically they are positive, which means it is outward radial direction. So this one we cannot predict it because in our model, we have a negative prediction of the radial flow. But in rush hour, as I said, our model can predict the process for the entire process pretty well until the very last moment, because ideally the particle, the droplet becomes flat homogeneously. But in reality, when it becomes very, very flat, some part has to detach first. It's not like perfectly goes down. It always has to detach from one point. And then the particles still not attached on the surface, some little particles on the upper surface, even it's very thin, but it has to go to somewhere. It flushes by the contact angle, detach it first. So for example, the left side first detaches, it will flush all this particle goes to the other side. This is called the rush hour. But this rush hour, we cannot describe in our theory.
Okay. Thank you very much.
Yeah, you're welcome.
So Yaxin, I have a question about the final stage of the evaporation, because based on your for example, this setup, you have a lubrication layer, right? So at the edge, I'm not sure in the final stage, this water phase should be covered by the silicone oil layer. So how this water will be evaporated after you have a silicone oil layer? Actually, then this means the water is not exposed to air, right? How this evaporation can continue to have reach to the last stage?
Yeah, this is also a very nice question. So actually, we discussed this in our paper, but because of the limitation of time, I didn't put in this talk, but I skipped the slides. Now I can show you. So this is a very nice question. So basically, you can see here. So you see this fringes. This fringes is because we use the interference technique. So because the silicone oil is so thin, so we use the two light to interfere with each other to see the patterns, then we can see the thickness. And for example, here you see the top column, the top row, you see this is a pure water droplet on the lubricated surface. Then you see eventually the very last picture, the third picture, you see those small particle deposition. It's already underneath the silicone oil. So basically the droplet shrink, become smaller and smaller until the very end, they completely gone. And then the silicone oil will fulfill this like a hole when it evaporates completely. Then the surrounding silicone oil will fulfill this little hole. And so in the most of the time during the evaporation, also, I guess you're asking about engulfment because I have engulfment fully covered on the surface. But this engulfment is very, very thin. Basically, it's just 10 nanometer or 20 nanometer. So people cannot directly measure it, but people use theory to estimate. So the thickness of this engulfment is very thin. So then it will not fully block my evaporation. So the water still can evaporate through this very thin engulfment by diffusion. So basically, instead of the water just diffuse into the surrounding air, it just has to diffuse through this very thin engulfment first, then go to the surrounding air. So basically, in this case, as compared to a pure water droplet case, if they have the same geometrical configuration, this case will evaporate slower than without engulfment case because it has to cross engulfment first. Yeah. And then for the second case, the surfactant-laden water droplet, you see because our contact angle is pink, contact line is pink. So we have the wetting edge. The wetting edge, as you can see in the second row, the last picture, it just goes down when all the liquid completely gone. So just touches the surface. And inside, it will leave the hole like this. But probably after a very, very long time scale, maybe hours, it will also fulfill this hole.
Okay, makes sense. Thank you.
Yeah.
Mr. Chair, may I ask a quick question? Hello?
Sure.
Please.
Yeah. Okay. Thank you, Dr. Lee, for the nice presentation. So for the three component evaporation case where you said, you have hexanediol, water, and the oil, right? You said you accidentally added some oil, yeah.
Yes.
And then you said because the oil is not miscible to the liquid, basically, so they nucleate first at the bottom, and then okay, yeah, and then you said this will be nucleation sites for for the hexanediol. Is this what you said? So
Yes.
I'm wondering, I'm thinking why this will help the extraction of hexanediol. So why hexanediol will be extracted, also nucleate on this oil, nucleated oil droplets, if you know what I mean.
Yeah, I know. This is a quite good question. Actually, this is what we put. So the first paper without the silicon oil, just hexanediol and water. So the segregation, we only explain it from the hydrodynamical perspective. We didn't talk about, for example, from the molecular perspective, how chemistry, how do they separate? Because we don't know. We only focus this on the fluid dynamics perspective. But we think, for example, as I said, the weak convection leads to insufficient mixing, then causes the hexanediol at the contact line regime becomes more and more. And then how do they segregate? Definitely need some nucleation point. For example, some dirt, some roughness. All this little roughness causes the segregation, just like a bubble. If you have a gas to liquid, but if you don't have nucleation, it will not form bubbles. So the bubble has to have nucleation, then they form bubbles. This is the same. But for this case, hexanediol plus water plus silicon oil, the silicon oil will first nucleate attached on the substrate and becomes many small little silicon oil droplet. And all these tiny droplets becomes the nucleation site for hexanediol. So basically, because for hexanediol, if you have a strong nucleation, will just like the chemical extraction, it will separate earlier than the previous case. That's our hypothesis. But if you really want to prove this physically or chemically, you probably need some other technique. But this is not what we want to focus because we are doing fluid mechanics. This is not our expertise. I hope you're satisfied with my answer. But yeah.
Thank you. Yeah, thank you.
Okay, any more questions? Okay, if not, let's thank Dr. Lee again. Thank you. We'll talk
Thank you very much
again, okay?
Thank you very much.
Thank you, Yashin. Then we will end here today.
All
Thank
right.
you all for
Thank you.
participating.